All right, so we've talked about nucleophile strength, leaving groupability, and the solvent and how that impacts the rate of an E2 reaction. But what we haven't talked about yet is the substitution of the alkyl halide. And what do we have here? We have a tertiary alkyl halide, secondary alkyl halide, and a primary alkyl halide. And we're forming different types of products too. We're forming a tri-substituted alkene, so this is tri-sub. We're forming a di-substituted alkene here, di-sub, and this is a mono-substituted alkene, mono-sub. So, E2 reactions, we know how they work, we know what the mechanism is. Which of these would you expect to proceed the fastest? And one thing I want to draw your attention to as well is in the course packet that you guys have now, in A, it initially said H2O here, but it was meant to say DMSO. So go ahead and cross out where it said H2O and write in DMSO like I have here. So pause the video. Which one would you expect to go with the fastest rate? And then unpause the video. All right, great. You've done that. One thing I want to first to think about is what makes something be a fast rate. And what makes something have a fast rate is a low activation energy barrier. And what that often relates to, not always, but often, is the stability of the product. And which of these is the most stable alkene? The tri-sub, the di-sub, or the mono-sub? All right, you answered yes. It's the tri-substituted alkene. So this is the most stable product, but would that have the most stable intermediate structure? And when you think about it, what happened here? Well, the OH minus pulled off that proton here, and the transition state for this top one would look something like this, where we're breaking that alkyl iodide bond. We are breaking the carbon-hydrogen bond here, and we're forming that pi bond in the intermediate. So essentially, the intermediate structure has alkene character that is tri-substituted. So this intermediate has, this transition state has tri-substituted alkene character. And just like the product, having the most substituted alkene makes it the most stable product, having it the most substituted intermediate partial alkene is going to make it have the lowest transition state structure. And that transition state structure relates to the activation energy. It's going to have a lower activation energy if that transition state is of a lower energy. And I show that transition state structure here as well in the course packet. We see the the transition state here, how that relates to the EA. That's what that transition state is. So how's that going to relate to the reaction rate? Which did you say was the fastest rate? Hopefully a lot of you, and this is usually the thing that people, of all the different things that we've talked about with E2 and rate, this is the one that is the least intuitive because it is the opposite of SN2. The other ones kind of back up what SN2 says. But this is, the more substituted makes it more challenging to do SN2 because the OH minus has a hard time getting to the antibonding orbital of the carbon iodide bond when it's more substituted. But we don't have to do that in E2. We're getting to a far out hydrogen. That is easier to access, so that allows E2 to still happen. So essentially, the more substituted the alkene product, so that I guess I'll even write that in, the more substituted the alkene product leads to the faster E2 reaction. And why is that? Again, that was because the transition state has that has a more substituted partial alkene compared to the less substituted products. So the last thing that's in your notes for this course packet page, is the characteristics of the E2 mechanism table. This is directly from your textbook, so you can see that there. But shows the kinetics are second order, like we said, bimolecular. The mechanism is a single concerted step. It shows what we just talked about, that a tertiary alkyl halide is going to be faster than a secondary, but faster than a primary. It's favored by strong bases and nucleophiles. Better leaving group is going to be a faster reaction, and polar aprotic solvents increase the reaction rate. So all things that we talked about in that one table. But don't memorize the table. Table's there, it's great. It backs up what we say, but you should be thinking through what each of those individual bullet points mean, and you should be able to reason those out. So hopefully you're not just trying to memorize little bits and pieces here, but trying to understand the whole, how everything's kind of working together. So yeah, so we're going to move on. Yeah, all right.